T now is the roof imposed load on the roof beams. If you want to see the intensity of these loads here, it's simple. What do you do? Right click, label, load values, apply. With this you can see the intensity of the various loads, on the structure. You can see the intensity of the loads on the structure. It appears to be, so you can see this is 1 kilonewton per meter. If you select any beam and you view it only, you can see clearly what is happening. So you see why you're seeing an overlap is because you have an intensity here. So this is a trapezoidal loading. So you have an intensity here and an intensity here. So it is close to each other, and that's why it appears as if it's overlapping. You see? Okay, so let's go back to the entire structure. You can always remove the label, load values. So we finished with the roof level. We move next to the 3rd floor. Let's make sure we haven't omitted anything. The next step is to do on the 3rd floor is the environmental load, the wind load. So we have calculated the wind load as previously done. So let's apply the wind load in the transverse and longitudinal direction between the 3rd and the roof level. So we have calculated the wind load in the longitudinal direction, which is in the x-axis. In the longitudinal direction, which is in the x, and then we calculate the wind load in the transverse direction. The code specifies that the loads must be calculated in the longitudinal and transverse direction, and that for doubly symmetrical section, you must apply the wind load in a minimum of 4 directions. Let's look at what the code states. BS 6399 part 2, just in case you are in doubt. Let's recall what the code states about wind load application. It's very crucial, so that we don't make a mistake. So BS 6399 part 2 Okay, see what the code is saying in section 2.1. It says that the code requires an assessment for orthogonal load cases for wind directions normal to the building, to the faces of the building, as shown in figure 2b. So wind directions that are normal to the faces of the building. So it means in 2 orthogonal directions. Look at that. That's figure 2b. So this is one face and that's another face. You can see there, this face and then that face. That's the requirement for the code. If you look more carefully, it says that when the building is doubly symmetric, as in the case of our structure, on plan, the building is doubly symmetric in terms of the geometry of the building. For example, it says rectangular plan with flat, equal, dual pitch or hip roof, etc. Now, it says that when the building is doubly symmetric, 2 orthogonal load cases is sufficient. So 2 orthogonal load cases, that's in wind load in the x direction and in the z direction, are sufficient. However, the code also specifies that you must consider opposite directions to the orthogonal. Look, it says when the building is singly symmetric, 3 orthogonal load cases are required. Example, for rectangular plan monopitch building, wind normal to the high eaves, wind normal to the low eaves, and then wind parallel to the eaves. So wind normal to the high eave, wind normal to the low eave, okay, and then wind load parallel to the eave. Then it says when the building is asymmetric, you have 4. Now it tells you that for each orthogonal load case, the range of wind directions plus or minus 45 degrees, either side of direction normal to the building face should be considered. When symmetry is used, so it's telling you that you should take wind direction in every 45 degrees. However, it says that symmetry can reduce these directions to 0 and 180 degrees. So this means that you apply the wind load in the x, minus x, z, and minus z. So let's start by, we have calculated the wind loads. It's time for us to apply these wind loads. So let's look at how it is done. Okay, so on the roof level, we calculate the wind load in the transverse direction, which is 0. Look at the windage area. The wind force was calculated. This is where the resultant wind force will act at the centroid of the windage area. At the centroid. So the wind load on each of the distributed joints will be the total force divided by those joints. And the wind load per joint is 5.7126. So let's create it. That's in the Z direction. Okay, so I will create wind load last. So let's leave that for now. Let's create the load cases on all the floors, and then we will treat the environmental load lastly. So let's go to the 3rd floor. Right. Now, on the 3rd floor, okay, so dead load, the total dead load, 6 kilograms per meter square. The total slab imposed load. So let's create the slab dead load on the 3rd floor beams. Let me create for imposed load as well too. Okay, slab dead load on beams. So what is the total load on the slab? So we see the self-weight of the slab, finishes, and then partition allowance. Total is 6 kilograms per meter square for dead load. We are defining the floor loads the way we did it previously. Maximum X here is 28.235. Minimum Z coordinate here is -1. Maximum Z coordinate is 10.275. Okay, say add, check it, you're fine. You see the intensity is huge because of the value of the pressure load you have here, which is about -6 as against 2.5 you had previously. So you have very huge intensity. So let's apply the slab life load on the beams. What is the slab life load pressure? 1.5, which is captured by the code of practice for access on residential building. So you go 1.5 11.4. So -1, 10.2. If you don't create this correctly, you're going to have problems. Once you try to add the load, it will not generate the floor load. So you must make sure you define the regions correctly. Now, there's something I need to mention here which we need to just pay attention to and note in structural engineering analysis. If you look at the third floor structural layout, you would see that in addition to the loads transferred from the slab to the beam, you also have load from these small cantilevers. So the load from this small cantilever is just the total loading on the slab times the overall length of the cantilever, which is this width. So you may choose to also calculate the loading associated with these small cantilevers. They are negligible anyway, but you may choose, if you have significant cantilevers all around the structure, the dead load. So what STAAD calculates is the loading from the internal slab. So you may want to add, because loading from this slab on this beam comes from here to here and here goes to there. So STAAD can compute that intelligently. Okay, from here to that and then from here. So all the, however, if you look here where we did not model the cantilevers, these cantilevers, you may want to compute the dead load and the life load and then get the reaction associated with that. So if the total load is Q and the length of this is L, the reaction here will be QL, and then the loading on this beam will be QL/2. So this is just, it's important to just note this, just for record purposes. Okay, slab on third floor. So what next? What are the other loads on the third floor? Let's go back to our loading. Slab life load. Have I done slab life load? Yes, that's 1.5. We've done that. What loads is the beams carrying? Again, the beams are also carrying beam finishes. So we're going to apply that same beam finish. This beam finish, you're going to apply it on the third floor. Great. The beams are also carrying wall partitions. Very important. Look at it here. Wall partition, wall load on floor beams. So we're going to assume that all the beams, if you look at the architectural design, it will show you which beams are carrying loads. But one of the issues with residential structures is that sometimes the client may change the intention and add additional walls. So you must have to cater for that unforeseen contingency in structural engineering design. So you would assume that the beams are all carrying walls, and the wall load, like we have calculated earlier on, using the specific weight of block work plus finishes, rendering on both sides, 0.6 millimeter rendering, or sorry, 12.5 millimeter rendering on both sides, each weighing 0.3 kilonewton per meter square as provided for by the code. The total wall load was computed as 2.87 plus 0.6, with 3.47 multiplied by the height. That gives us the wall load on the beam. So you're going to apply that, which is 10.9. So it creates a load case. .931. So take it, apply on the entire beams. We assume that all the beams are carrying walls. Wow, that's great. So this is on the third floor. Which other loads on the third floor? So that's all. So these are the same loads on the second floor. Okay, so second and third floor are the same. Second and third floor are the same loads. Okay, so similar loads apply on the second and third floor. Okay, second and third floor. Okay, so I have just seen an error which we have done. If you look carefully, on the third floor, I have used a pressure load from the slab to the beam. I have used, okay, so 6 kN/m square is the same. Let me look carefully. You see, you always have to check your loadings to ensure that it's correct. So this is on the first floor level. We are having total dead load as 6 kN/m square, and then we have input load 1.5, so we are fine. That's quite correct. But take note that anywhere you have your slab to be of a different thickness, your total dead load will change. Anywhere your slab is of a different thickness, the dead load on that floor will change. Or if the floor is not a solid slab, if it's made of composite material, the total dead load will change. This is just to note this information. So we move to the second floor. Let's go to the second floor. So slab dead load on beams on this floor. Okay, so slab dead load on beam. So you go to floor load. So these are the load transferred from the slab to the beam. Always take notes. So total dead load here is 6 kN/m square. So you say -6, it's acting downwards. And then come here.